Okay, in this YouTube video we're going to get an introduction to the chemistry of aromatic compounds, which was an entire functional group class of compounds including its primary member, benzene. Benzene is a six-membered ring in which you have six carbons, each of which has one hydrogen on them. I'm just drawing one of them here. And a formal double bond and single bond is shown from that carbon. We learned in the first quarter that in fact there are two equally valid resonance forms for benzene, and that you can show the double bonds between either set of alternating carbon atoms. Each of these carbon atoms is sp2 hybridized, and each of these carbon atoms is identical. All six are exactly 1.5 bonds in length, and all of them are the same size and the same strength. Sometimes that is represented by the Kekulé structure shown on the left, which is actually a representation of the resonance hybrid of the two contributors shown. Now we can also think of benzene in terms of the orbitals that make up the six-membered ring. I'm going to redraw the six-membered ring, this time looking edge on. And each of those carbon atoms has a p orbital on it. It's sp2 hybridized with one p left over perpendicular to the ring. And those six p orbitals overlap to form a net set of molecular orbitals above and below the plane of the benzene ring. That is the pi molecular orbitals. In order to have this kind of delocalized bonding, as represented by the two resonance forms here, you must have a fully conjugated system. That is, you must have a series of sp2 atoms next to each other. Okay, so in this particular compound, it is a cyclic compound with alternating double and single bonds, sp2 on every center. It's what we call fully conjugated. In the chem activity, this will be designated by drawing the racetrack going around the inside of the ring, where benzene has a continuous racetrack. And we will also be counting electrons within the ring, particularly pi electrons. And the pi electrons on benzene are the ones that make up the three formal pi bonds. So there's 2 electrons here, 2 electrons here for this pi bond, and 2 electrons for the third pi bond. Altogether, there are 6 pi electrons in the benzene ring. In the chem activity, we will be counting pi electrons quite a bit. Not every conjugated system is part of a ring, but they can be. Here we have a conjugated system that makes up part of a ring. We have sp2, sp2, sp2 nitrogen, sp2 carbon, all next to each other. This nitrogen is sp3 and is not part of the pi system. So this molecule would not have a racetrack. It does, however, have a conjugated pi system, and we can count the pi electrons. There are 2 electrons here, and there are 2 electrons here, for a total of 4 pi electrons. Why didn't we count this pair right here? Well, it turns out that this nitrogen atom is already involved in a pi bond with the carbon next to it. Therefore, it's already using up the space of its p orbital and doesn't have room for another 2 electrons. Those 2 electrons, in fact, are in an sp2 orbital. The next structure is not even cyclic, but it does have an extended conjugated system. Here we have sp2, 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 all the way up to the oxygen sp2. And we have a total of 2, 4, 6 pi electrons. In our final system, also not a ring, we have sp2, 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 and the last one, the last atom, has a pair of electrons in it which can be rehybridized into a p orbital to make another sp2 position. So in fact, every single atom in this chain can be sp2 hybridized for delocalization. and we can draw resonance forms in which the extra pair of electrons and the negative charge end up at other positions. Here there's a total of 2, 4, 6, 8 pi electrons, because in order for this last carbon atom to be sp2 hybridized, the lone pair of electrons must go into the p orbital. In the chem activity, you will have a chance to practice when to count lone pairs of electrons and when not. In general, if you have a pair of electrons on an atom that already has a pi bond to that atom, that pair of electrons cannot be part of the pi system. This is because that nitrogen atom, in this case, already has a p orbital involved in the pi bond, and therefore can't accommodate an extra pair of electrons. The same is true for the two pairs of electrons on the oxygen atom in this part of the pi system. Because there's already a pi bond, there's no room to put additional pairs of electrons into a p orbital. On the other hand, if you look at the structure on the right, the atom on which the lone pair resides does not already have a p orbital. In fact, the only way that this atom can participate in the pi system is by placing that lone pair of electrons into a p orbital. And once that pair of electrons is in a p orbital, it is able to overlap with all the other p orbitals in the conjugated system to delocalize. So let's go back to why benzene is so special. Why is it benzene and its double bonds are different from other things with double or pi bonds in them? And to do this, we're going to start by looking at the extraordinary stability of benzene. Cyclohexane has no CC pi bonds and is reasonably stable, all the way down here in energy. Cyclohexene has one pi bond, and in general, pi bonds are less stable than the corresponding sigma bonds. So if I were to take cyclohexene and add 2 H's in the presence of a palladium or platinum catalyst, I could make cyclohexane, and I could measure how much net energy is released, and it turns out it's almost 120 kilojoules per mole. So you might imagine if you had 2 pi bonds in the ring, it would be twice as much. Twice as much as 118 is 236, and in fact it's very close to that amount, is how much energy is given off when you hydrogenate cyclohexyl-1,3-diene. Here you have 2 pi bonds, and it gives off almost twice as much energy as hydrogenating 1 pi bond would. So if you follow the same analogy, you'd expect benzene, with its 3 pi bonds, to give off 3 times as much energy. Negative 356 kilojoules per mole would be expected. But when you do this experiment, you find out something very unusual. First off, if you just add hydrogen at room pressure, room temperature, and palladium, conditions that are adequate to hydrogenate cyclohexene, cyclohexadiene, you'd find that benzene doesn't react at all. It's extraordinarily stable. But if I insisted on making this reaction work, so I heated the reaction to a couple hundred degrees, I increased the pressure of the hydrogen, I could eventually overcome the kinetic barrier to the stability and hydrogenate all the way to cyclohexane. And when I do that, I do get a net release of energy, but not nearly as much energy as I expect. I expected 356 kilojoules per mole. When I do the experiment, I find that I only have 206 kilojoules per mole given off, not 356. In fact, there's 156 kilojoules less given off than I expect, and that tells me that the benzene is not up here in energy, not real high. In fact, is way down here in energy. It's actually more stable than cyclohexadiene with 2 pi bonds. This extraordinary stability means that benzene behaves differently in chemical ways, and that's why benzene has its own functional category.